Hi everyone, and welcome to this tutorial bite for Oxygen Not Included, which is a complete guide to sour gas boilers. These are what I consider the most advanced of the commonly built designs in the game, and is highly challenging and rewarding. I'm going to cover the process, and why they're so good, as well as how to build and run them. But before I go straight into the process, I need to offer some warnings. These are advanced builds. They need space materials, and can take a long time to set up, so you'll need to run your base at the same time. I will also say that even trying to exactly copy the design as I show it may not work easily, because of how sensitive they are. But if you can make sustainable bases, and get space materials, then please don't be put off, as the sour gas boiler is really powerful. So let's look at the process, and like the petroleum boiler, we start off with crude oil. The boiler I'm going to show is for a 10 kg per second oil input taken from 3 oil wells fed with 3 kg per second of water. I explained oil wells fully in their own tutorial bite. Also, like the petroleum boiler, we will heat the oil up using a heat source, but this time we don't stop at petroleum at just over 400 degrees Celsius, but continue to make sour gas at 540 degrees. Now, to get a useful product from the sour gas, we need to cool it down into a liquid, which happens at minus 163 degrees Celsius, so a change of 700 degrees. When we do cool it, we get 2/3 liquid methane and 1/3 solid sulfur. The sulfur output alone is enough to feed 100 sweetles, or fertilize 200 grubfruit plants. This alone gives food outputs of around 60,000 kilocalories per cycle focusing on barbecue, or 50,000 kilocalories per cycle focusing on grubfruit. But there is much more, and the liquid methane is easily heated up to over minus 160 degrees to make natural gas. For numbers, this gas output will feed 74 natural gas generators, and this is 75 if you include the natural gas from the oil wells too. The power output from these alone is a huge 60 kilowatts, which is 20% more than even a heavy watt conductive wire can draw without overloading. I've estimated a maximum power draw to run everything at around 10 kilowatts, leaving a net gain of 50 kilowatts. Then the byproducts are also large, and these generators will produce around 1.7 kilograms per second of carbon dioxide and around 5 kilograms per second of polluted water. If we take this polluted water and turn it back into normal water through an industrial brick, this means the boiler will again sustain itself and produce an extra 2 kilograms per second of water. For the carbon dioxide, this can be fed to slicksters and will sustain 50 of them by itself. This means more food output, in practice making around 30,000 kilocalories per cycle if turned into barbecue. Plus, these will produce enough petroleum to run another petroleum generator a bit under half the time, which brings more power, carbon dioxide and water. So looking at these numbers, the sour gas boiler is extremely powerful, and more so than even the petroleum boiler. If you get this running reliably, you'll almost certainly never run out of food or power. And speaking of that, let's now look at my design to understand how to take the oil, boil it, condense it, and reboil it again. I should quickly note that there is no standard design in the community, and there are many ways of achieving the same process. The key to this design is a double heat exchanger, and the first runs the incoming oil against the sour gas produced. By heating the oil and cooling the sour gas, less heat needs to be added to boil the oil and less taken away to cool the sour gas down. This design uses a bead pump, in which the liquid is output onto a mesh tile, then falls between 2 walls. As the liquid falls, it pushes the gas up and exchanges heat all the way down. There are diamond temp shift plates and thermium metal tiles to help the heat transfer. At the bottom is the heating area, which I will explain shortly. The second heat exchanger is between the sour gas and the natural gas final product. Again, there are thermium metal tiles and diamond temp shift plates, and note the spacing is 3 apart to reduce heat flow along the gas path. At the bottom is the cooling and condensing area, which I'll also get to shortly. Once liquid methane is made, a liquid pump moves it across. Then natural gas is made and flows to the gas pumps, Remember that this makes just under 7 kilograms per second of natural gas, so 14 pumps are needed. These should be made of steel or thermium to avoid overheating. The gas output really needs to go to an industrial brick to be properly handled, and I'll also look at a design for this at the end of the video. So having gone through how the materials flow through the boiler, let's look at how the bottom area of this design manages the heating and cooling. I'm using 4 aquatuners here that heat the surroundings and will be used to boil the oil as well as cool the coolant that is used to condense the sour gas. Note that theoretically this could be done with only 1 aquatuner, but the fewer aquatuners used, the larger the design needs to be to increase the heat exchanger efficiency. It's also important to point out material choices here. As the oil fully boils at 540 degrees Celsius and the sour gas condenses at -160 degrees, the aquatuners must be made of thermium and supercoolant must be used. These are space materials, and for more information on how to get these, see the dedicated tutorial bite. For heating to boil the oil, the aquatuners add heat to this steam room. There is then a heat injector, which is a mechanised airlock between 2 layers of metal tiles, all made from thermium. When more heat is needed, the thermosensor closes the door, otherwise there is a vacuum, so no heat is transferred. The setting I'm using for this thermosensor is above 560 degrees. On the right side is a steam turbine, which is turned on if the steam room gets too hot. This is controlled with a thermosensor set to above 800 degrees. Note that this turbine is cooled by the main cooling loop and returns water close to the aquatuners. It's important to use hydrogen gas as the atmosphere for this, as most other materials would freeze at these temperatures. Also note the material choices for automation sensors and automation and power wires in this area, as lead and aluminium will both melt. The aquatuners also have their own automation and have 2 conditions to turn on. If disabled, there is a bypass to continue flowing the coolant. The first condition is simply if the steam room is too cold, so a thermosensor set to below 700 degrees. And the second condition relates to the cooling area for the sour gas, which is done here. Airflow tiles bring the gas in and reduce the heat transfer out of this small room. I've used copper ore for these. Once in the cooling area, the gas is cooled to liquid methane by the thermium metal tiles, and then pumped out above to flow back against the incoming sour gas. The main cooling loop runs through the metal tiles, and a small area of supercoolant with a liquid tepidizer in. This prevents the area from getting too cold and is controlled with a thermosensor set to turn on below -180 degrees. The second automation line to the aquatuners is also taken from this sensor, and will keep the aquatuners turned on if the temperature is not below this. In the solid shipping overlay, you can see the auto sweeper and conveyor loader that brings out the sulfur produced to be used for food production. There are also conveyor rail bridges made from thermium that are used for heat transfer only. So that covers how this design of sour gas boiler works. I'm now showing the full one-take reference for this design if you want to recreate it. And as the build is large and complex, here are all of the layers individually. Note the 4 diamond temp shift plates in the condensing area. For some further help, I'm now going to briefly cover building and starting up the design. It's important to start by saying that you should vacuum out the entire area first. This is why the easiest place to build this is just below the space exposure at the top of the map, as this will vacuum the area itself, but you won't need lots of drywall. The way I would suggest building this design is by planning in all the wires and pipes, then build most of the design, including ladders and gaps for access. Here is an example of building most of the design in a first pass. Then add layer by layer the remaining tiles. Starting up this boiler isn't too challenging because of the design. Remember to fill the key areas, supercoolant around the tepidizer, hydrogen behind the steam turbine, and water in the steam area. For quantities, 400 to 800 kilograms per tile of supercoolant is needed. The hydrogen can be left at 2 kilograms per tile when the gas vent overpressures, and I aim for around 200 kilograms per tile of water on the bottom layer. Fill the supercoolant loop by bridging on to ensure it doesn't jam. With these set, close up the walls and add some oil to get started. Around 200 kilograms per tile will work well. Set the sensor values, then turn the system on and let the supercoolant reach its minus 180 degrees and the steam room around 700 degrees. Note that you will need to provide quite a significant amount of power to get this started. Once the steam room reaches around 700 degrees, you can now enable the full flow and it should run sustainably from here. The final points to cover are dealing with the outputs, starting with the natural gas and recovering the water. This really needs to be done in an industrial brick, and I explain these in depth in their own tutorial bite. There are really two options to deal with the polluted water produced, either boiling it in a large hot industrial brick, or using a cold industrial brick and boiling the water elsewhere. A hot industrial brick, as shown here, is simpler, but 75 natural gas generators will require 60 tons of steel or thermium, which is a lot. If you don't have this, then collect the polluted water at the bottom and cool the generators with a cooling loop. Then boil the water elsewhere, for example using aquatuners, as I covered in the heating tutorial bite. Remember that this design produces 5 kilograms per second of polluted water, so a water sieve will use large amounts of sand, making boiling by far the best way to recover the water. There are also some logistical challenges with connecting this up, both the gas pipes and power wires. The boiler outputs 7 gas lines, that each need to be connected to 11 generators. Having 7 floor levels in this brick is a good way to simplify this. Then there's the carbon dioxide output lines. You'll need 2 of these, so divide the generators roughly in half and connect them up. This carbon dioxide is best used in a second industrial brick to feed slicksters. Power wiring is another challenge here, and this brick will generate 60 kilowatts of power, which is more than the 50 kilowatts a single heavy watt conductive wire can take. The simplest way to deal with this is to split the output into 2 lines and run these as separate circuits. For this hot industrial brick design, I thought I would also include a one-take reference to help, as well as the individual layers. There is a more advanced way to keep all the generators on the same circuit by using power shutoffs, smart batteries and wattage sensors. The 50 kilowatt limit only applies to consumers, so we can connect all the generators here on the left side. Then this connects to separate heavy watt conductive lines with consumers on and charges the batteries on these lines at different times. To do this, a smart battery will close the shutoff to charge the line when needed. The smart battery setting here is high to keep the charging time short, so 70 low and 80 high. I've also included a second shutoff connected to a wattage sensor, just to protect against the case of multiple circuits requesting charge at once. If the sensor detects over 50 kilowatts, then it will disconnect the line to prevent overloading. And finally, the last output to mention is the sulfur, which is brought out on a conveyor rail. It should be fairly straightforward to deliver to grub fruit and grub farms, but be aware that this comes out at minus 160 degrees Celsius, so you'll need to heat the sulfur or the farm. For more information on solid shipping, see the dedicated tutorial bite. So that's everything for this complete look at sour gas boilers. I hope this encourages you to give this advanced build a try, and thanks for watching.